You're live, Rob. Go.
Hi everyone, Rob here from MTU's Black Rock Castle Observatory, and welcome to the Hodges Effect, our Radiant Point. This event is being viewed live at the University of Alabama and virtually at University of Florida, the Signal Arts Center, and here at Black Rock Castle Observatory. It's a really incredible story that we're sharing with you tonight, the story of Ann Hodges. It's one that here at BCO we find particularly thrilling, given our obsession with looking at near-Earth objects. It doesn't get much more near-Earth than when one comes flying in and hits you. So it's going to be a pretty exciting story to hear from our three experts on. The first of our speakers tonight will be Sean Taylor, who is a socially engaged artist and educator. His collaborative practice engages with social and environmental issues through sonifications, multimedia artworks, and situated public performances. He holds a PhD exploring the practice of acoustic listening and the creative sound walk, and its links to the social and creative reimaging of place. Sean Miller will also be joining us. He combines art making, curation, collecting, and experimental exhibition formats in his work. In 2022, his exhibitions include Fluxus, 60 Years in Flux, via the Croce Museum, Italy, Biophilia, University of Minnesota, Morris, and the Exquisite Moving Corpse collaboration with Chip Lord, Jack Massing, and others at Palace Projects, Ireland, Archivio Emily Harvey, Venice, Italy, and Scope, Miami. And finally, we'll be hearing from Dr. Julia Cartwright, who's an assistant professor at the University of Alabama in the Department of Geological Sciences. Her research area is planetary science, where she uses petrographic and geochemical analysis of meteorites to understand solar system processes. So enough from me. Let's head over to the real experts, starting with our good friend, Sean Taylor. Sean, how are you doing?
Fine, thank you. And let me start by wishing everybody a very, very happy Ann Hodges International Meteorite Awareness Day. I'm just going to share my screen here and we'll kick off. Okay, hope you're all seeing that. Okay, so as you all know, on November the 30th in 1954, Ann Hodges was struck by a meteorite while sleeping. The meteorite crashed into her home and bounced off a radio and hit her on the hip. Despite being bruised and shaken by the incident, she survived and simultaneously became the first, and so far, only recorded human to be directly struck by an extraterrestrial object. So, what might you say? Space materials fall on this planet on a daily basis. Was Ann just random space bait? No was the answer. What Ann was not aware of at the time was that her interaction with the extraterrestrial object unleashed a molecular cause and effect condition known as the Hodges effect. In his writings, and particularly in the Third Policeman, which the copy behind me, if anyone can see it, the great Irish armchair philosopher and writer Flann O'Brien took scientific principles, extrapolated them to fantastic proportions, and set the outcomes in a bizarre context that are once both logical and illogical. In this book, the narrator is continuously challenged by scientific processes that we normally take for granted, such as the relationship between space, light, and time, the conversion of energy, and perhaps most famous, Flann O'Brien's molecule theory. Flann proposed the notion of the molecule theory, which describes how the molecules of people who spend a lot of time on their bicycles cycling over bumpy roads becomes merged with the molecules of the bicycles themselves through an interaction of heat through their behinds and the saddle of the bicycle. In Ann's case, the displacement of molecules from the meteorite and the subsequent bruising on her hip became the site of an exchange of human and extraterrestrial molecules. There can be no doubt that Flann O'Brien's molecule theory laid the groundwork for the Hodges effect. The effect also results from space travel, space research, or through direct interaction with or experiencing cosmic events or materials. It is speculated that Ann Hodges was exposed to high levels of the Hodges effect on the night of November the 30th, 1954. Although the effect is known to contribute to angst, mental disorientation, and religious fervor, as Ann said herself, I think God intended it for me. After all, it did hit me. There is a further possibility that the psychological effects contained in space dust and meteorites may be transmitting the Hodges effect through visual aspects and methods. The effects are spread through contaminations solely based on visual stimuli relating to their form and shape. It is further surmised that to see or hear the effect may run the same risk as the danger of physical contact. Even a slight look at a photograph of a micrometeorite, for example, or Ann Hodges herself, or contact with someone who displays symptoms of Hodges may be enough to cause a risk of and trigger infection. The visual structure in the virus effect system strikes the eye and transforms its information in the human brain back to a subsequent living condition that will attack certain parts of the body. Surprisingly, in many cases, the after effects of Hodges seems to imbue individuals with a greater spatial awareness, an increased sense of interconnectedness with the cosmos, and a more complex and informed understanding of the material world. I believe that further research into Flann O'Brien's molecule theory, the Ann Hodges case, and research into object-oriented ontology may provide a foundation for a better understanding of the Hodges effect phenomena. Creative practitioners such as Marcel Duchamp, Orlan, Captain Beefheart, jazz great Sun Ra, astronaut Edgar Mitchell, and others may have benefited from their undiagnosed Hodges effect condition. Philosophy, if we turn to that for a moment, offers us yet another perspective on Ann Hodges herself and her changing behaviors post Hodges effect. We may concur that exposure to the Hodges effect enabled Ann to function as a contemporary rhythm analyst. In his publication, Rhythm Analysis, Space, Time, and the Everyday Life, the French philosopher Henri Lefebvre introduces us to the concept of the rhythm analyst, an individual who analyzes and comprehends their interrelations between the temporal and spatial order of rhythms in everyday life. He defines the rhythm analyst as one who listens to the body, as one would listen to the world. Rhythm analysis relates to the cyclical rhythms that are revealed in our immediate environment as experienced through the physical senses. Investigating and revealing these rhythms better informs our understanding of life. A critical departure point for Lefebvre's analysis of rhythms is, of course, the human body. In particular, listening to the body's intricate rhythms, its relationship to nature, external rhythms, and its sensations. According to Lefebvre, the rhythm analysis draws on his breathing, the circulation of his blood, the beating of his heart, and the delivery of his speech. The complexity of rhythmic fields presented in urban environments as a result of extra-terrestrial contaminations, therefore, may be considered as examples of what Lefebvre refers to as polyrhythmic fields. Lefebvre states that rhythm analysis thinks with his body, not in the abstract, but in lived temporality. So, in applying a rhythm analysis approach to Ann Hodges' experience, we can then ask, how did Ann listen to these common and mundane elements and rhythms that constitutes a soundscape? How did she direct her senses towards movements among people and in nature? Was she even aware of her new skills? How did she creatively construct these spaces of listening, and how did she assign aesthetic meaning to them? We may even refer to Ann at this juncture as some sort of idiot savant, a person who is extremely unworldly but displays natural wisdom and insight. Lefebvre offers further clues for the nascent Hodges effect rhythm analysis through a kind of rhythmic temporal sense of space. Go deeper, dig deep beneath the surface, listen all attentively instead of simply looking or reflecting the effects of a mirror. He will come to listen to a house, a street, a town, as an audience listens to a symphony. A kind of an interesting analogy for the Hodges effect. Ann's epiphany may be further underpinned by Lefebvre's contention that time and space, the cyclical and linear, requires a dialectical relation to encourage us to perceive in a particular way. Lefebvre's methodology highlights the importance of observation through careful analysis of rhythms to reveal our association with time, space, and energy. This social place is a space where Ann consciously used and transformed the information of both the astral and the everyday. Lefebvre's concept about rhythm analysis remains dispersive and unfortunately incomplete. However, it is my contention, and the subject of my personal ongoing research, that they offered Ann a nascent skill that enabled her to frame and study the dialectics of power in her urban setting. particularly in the interrelations between the body and everyday life within our capitalist society. Of course, if we follow this particular line of inquiry, we may further suggest that Anne's condition and the understanding of it is a form of hyperobject. Timothy Morton refers to hyperobjects as things that are massively distributed in time and space relative to humans that confound our limited, fixated, self-orientated framework. The Hodges effect, then, despite being so defiantly caused by extraterrestrial interactions on a molecular level, is so profoundly non-human, so expansive that our understanding is continually outpaced by its total seepage into our environment. Why is that? Good question. The reason appears both speculative and multifaceted. We live in a post-industrial capitalist mediated world of information overload where our very enjoyments are commodified and sold to us. And just like Ann Hodges, we are thus reduced to passive and disconnected spectators of our own lives. The Slovenian philosopher Slavoj Žižek states, what is really hard for us, at least in the West anyway, to accept is that we are reduced to the role of a passive observer who sits and watches what her fate will be. To avoid this impotence, we engage in frantic, obsessive activities. We recycle old paper, we buy organic food, we instill long-lasting light bulbs, whatever, just so we can ensure that we're actually doing something. The journalist Lucy Jones explains, simply put, we've moved inside. We live in cubicles, cars, and tower blocks, spending only 1 to 5% of our time outdoors. I suggest that this is both the cause and effect of not taking Ann Hodges or the Hodges effect seriously. For Ann Hodges, outer space suddenly became jarringly present, close enough to forcibly impact someone in the privacy of their own home. The Hodges event provides the backdrop to recognize the important role that meteorites and cosmic collisions in general have played in the evolution of our planet and of ourselves. Just as one collision changed Ann Hodges' world, countless collisions continue to shape our world. So, what do we do? What can be done, as Vladimir Lenin once said famously before the whole communist system collapsed in a day? Well, we raise awareness, don't we? How do we do it? Well, we organize. We bring pressure to bear on those whose intergovernmental organizations, whose stated purposes are to maintain international peace and security, and who develop friendly relations among nations, who achieve international cooperation, and then possibly we can be a center for harmonizing the actions of nature and nations. Where do we start? Of course, we start at the very top, the United Nations, that august body of people who never really seem to get much done, but do an awful lot of talking about getting things done. So we started a petition for Hodges and for Hodges awareness, and for a day to be created in Ann Hodges' memory, because after all, this project is about Anne, and it should always be front and center about Anne. So we wish to mobilize, support, and work with decision makers to make November the 30th the International Ann Hodges Meteorite Day going forward. So how can you do that? Well, it's very simple, really. You read and familiarize yourself with the declarations of principles for activities following the detection of Hodges effect. This will give you an insight into the effects and some of the causes that you might notice in yourself or in others. So then you take a copy of Irish authors Flann O'Brien, The Third Policeman. You can lend it to somebody you know, and based on their reaction to its contents, you can decide whether to accept them as a friend, or you can downgrade them to an acquaintance, or if you really don't like it, you can drop them completely. Most importantly, write letters of support and sign the petition. Thank you very much.
Thank you, Sean. Okay, I think it's time now to go to our good friend Sean Miller. Can you hear us there, Sean?
Yeah.
Yeah.
We're getting mic'd up. Can you hear me okay?
Absolutely. And we can see your screen too. It looks great.
Great. All right. Well, thanks, Sean, for getting us started. And also, I wanted to just thank University of Alabama and University of Florida for helping coordinate this, and Black Rock Castle Observatory and Signal. It's been great to be here for the last couple days researching more about the Ann Hodges in the archive. And so, you know, we talked a little bit about like what the Hodges effect is and how it affects us. And I also wanted to just introduce some of the ways that we are trying to like reach the public and maybe safely induce the Hodges effect. We know the story, Ann Hodges being struck. These are images, and also I should say that our collaborator Connie Wong isn't with us today, but some of the graphics and things that we're showing are the benefits of her design skills, and this will give you the kind of the Hodges effect, the exact kind of definition of the Hodges effect. It's physical changes and or existential crisis of being that may occur after sudden collision between a Homo sapiens subject and extraterrestrial materials. The Hodges effect is an emerging concept in the domain of Homo sapien encounters and responses to environmental change. And these are images from some of the billboards that we had in Cork last year during Space Week. And I've been working a lot with Ann Hodges illustrations for our field guide for hurtling through space, which I'll talk about in a minute. This is one that I'm working up right now. A lot of the images of Ann Hodges that we see, you can tell that she's been thrust into this situation. And so a lot of when I do illustrations or work with re-envisioning her, I like this one, for instance, my wife said she looks like a badass. And I kind of liked that because she is a hero of mine in a way for being thrust into this and kind of being a stand-in for all of humanity by being struck by an extraterrestrial object and then having to respond to that to everybody that wanted to hear about it. And so we did these billboards and have started writing letters. Right now at the College of Fine Arts in University of Florida, we have a display up with multiple that I'll show more images of right at the end of the presentation. But we have one of the letters of to the UN handy so that people can look at it and consider writing their own. The dean of the college as well as the director of the School of Art and Art History have agreed, and that's kind of part of what I'm doing here in Alabama, is starting to now work with some of the faculty here to begin writing their own letters to the UN. I think Sean's plea, the other Sean's plea, to begin to do activist work. We do have a petition to sign, and I'm putting this up because I know it's being recorded. So you have a QR code now that'll take you directly to the petition, which just takes a second or two to enter your information and get on board for. So I would encourage everybody who's watching this today to take a moment and do that. And the title of the talk today is The Radiant Point, Our Radiant Point. And this is an illustration that I did for the field guide for hurtling through space, where Ann Hodges is holding a meteor shower diagram with a radiant point in the center. Radiant point can be described as the point from which all meteors appear to emanate during a meteor shower. It arises as a consequence of perspective. So if you're looking up in the air right now and the radiant point is above you somewhere, all these arrows will be streaks going through the sky looking like they're going in different directions. But in reality, from Earth, they'll all be on a pretty parallel course. And I think Julia will probably talk about that more and is obviously the expert. But I just bring it up because we're using this as a term, because it's also, we're talking about a certain kind of a metaphorical response that we're hoping we can create a radiant point with a response to the UN and these petitions, so we can grow in numbers in terms of wanting a day where we acknowledge meteorite awareness. And these are more of the give space a chance, were some of our slogans from last year, and it's okay to experience the Hodges effect, which we're all up in court during Space Week, our sign from the heavens. And this actually has a replica of the Hodges meteorite space available. And we also have been, to kind of safely spread the Hodges effect and induce it in the public, one of our performances that's been done in Italy and Ireland and the United States in several different instances is the meteor drop, where we take a meteor that I've constructed or recast from the original, and then we infuse it with space dust, and then make a plaster mold of it and throw it at an institution or a building to try to create and induce a Hodges kind of situation there. And it's really interesting because the Hodges meteorite gained its value. One of the reasons why it gained its value is because it actually struck a person. It's not that it's a especially special meteorite, but it's interesting how reverent people are towards the cracked, broken pieces of plaster that are on the ground afterwards, because they feel like something's really important. That's Jade Dellinger and another member of the staff at the Bob Rauschenberg Gallery writing letters as I drop a meteor last year. Recently, some of our outreach materials have started to show up in New York City and other cities, which link to the petition to try to encourage people to join us in our campaign. These are the two of the designs that we came up with this year for the project. Also newly released and complete is the Hodges Effect Kit that helps educate people on the Hodges Effect and learn how to different ways to have exercises that will allow for Hodges to occur. Here's an example of the kind of the wrap that goes around that you can put the address on. It includes the field guide for hurtling through space, which is like a zine, a comprehensive zine that talks about the history of and associations with Hodges and ways to induce Hodges safely. Just some of the design pages. So some of the things that we've come up with are scores so that people can perform different actions that will create Hodges. This one is the score for fallen stars, and all you have to do is sprinkle space dust, which comes in the kit with it, onto the score to create a chance musical Hodges sound piece. There's also space peeps, which are just exercises you can do with handheld meteors, much less jarring than being hit by a 7 or 8 pound meteor. You just like hold them in your hands and do these and do these different actions. It's okay to explore Hodges, the wish space piece, and others. Also, I don't think I'm going to be able to show you because I'm kind of a shadow, but there's also these patches which I'm wearing today, the Hodges effect patches. There's also, like, you can see the meteorite with space dust, and then also there's kind of a black circle in the middle here, which is an image that the Black Rock Castle Observatory gave us, which is made in a coaster form. So you can put your coaster on the table facing the sky, and the stars that are on the coaster are actually what the sky looked like at between noon and 2 o'clock when Ann Hodges was struck by the meteorite. So just to show where the Sylacauga is in Alabama, you get a sense here. This is Sun Ra and Edgar Mitchell showing us where it is within Alabama. Both spent time in Alabama's and were considering space in different ways, but equally, I think, important in many ways. And this is the meteorite itself, a very detailed image of it. So let's imagine now that we're somewhere over Alabama, and we're kind of moving downward toward Sylacauga. And this is basically the current day site where Ann Hodges' house once existed. It kind of crashed down there. And tomorrow morning, after I get done doing more research here, I'm going to go out, and I have Hodges meteor replica that I'm going to kind of give a toss in that area. Hopefully nobody that's living there is going to have problems with that, but I want to get a good picture of that on the day as an anniversary kind of response. And here's exactly where it was in the house. Yesterday when I was in the archives, I found this picture, and I hadn't seen this before, but you get that arrow. I think this was in Life magazine, and it shows you exactly where the meteor struck the house. And of course, we already saw the image of what happened coming through the house. And just to read Ann Hodges' response to that, it could have happened to anyone in the world, but out of some 2 billion people, it happened to me. Like there were 2 billion people in that at that time when she was on the planet. I can't describe the sound, like the whole house exploded. I jumped up stunned and then heard another noise. It was then that I felt the pain flaming up through my left hand alongside my hip, and an object had fallen from the quilt. And the second noise I heard was it striking the floor. I stared down at the thing that had exploded into my life. It was a rock, not even a very large one, about the size of a cantaloupe. I stooped down to try to give it a lift with one hand, and I couldn't. The meteorite was warm and heavy, and it was like it had been roasting, you know. So like this is her own response to this event, and you could tell, you know, she was shaken. This is a detailed picture of the actual radio that it struck that's here in the collection with the actual meteor on it that I took yesterday. And here's the radio, still pretty good shape. It doesn't play anymore, but structurally it didn't do much when it got hit, when it came through the ceiling. So the thing that gives us, you know, she'd probably gotten done with Thanksgiving. She was like, you know, taking a nap at noon, between noon and 2, and got struck. But you get a sense of how close away now December 1st is from today. And there's a barrage of letters and telegrams already coming through to her to try to encourage her what to do and ask questions about it and to save the meteorite. There's a dispute that happens over the meteorite with her landlord, and it's just an amazing story. This is I've Got a Secret, like within the December of 1954, she was on TV shows like I've Got a Secret, which she didn't really want to do, but she did. She was kind of people encouraged her that knew her to go on the show. So she got even more notoriety and didn't really want any of that. And the last time I was here researching this, I ran across this. There was some space launches going on on the exact day when I was here researching, and I ran across this win a trip to space question. And then I was also researching more Timothy Morton, who obviously through object-oriented ontology has a say in I think about ways to think about space and our place in the cosmos. And he has a lecture that he gives called Why Don't We Try Landing on Earth for a Change, talking about how before we get too excited about space, we could start to learn more about the flora and fauna and other things that happen on this planet and how those things are interconnected and we're a part of it and not necessarily special to it. He says that's what we are, alienated from Earth. We've already gone to Mars in a way. That's like what we sort of do all the time with our politics, our ideology, and religion. I say to someone like Elon Musk, why don't you try landing on Earth for a change? That might be a good idea. Why don't we try landing here where we actually are? It's much simpler. All you have to do is get rid of the stupid idea that is what is wrong, is that you are a special separate being called a human, a being different than chimpanzees, dolphins, and bacteria. That's not true. We coexist in this in a symbiotic way. It's an uneasy thing. Beauty is a strange and uneasy thing, which I thought was a really beautiful statement. The idea of beauty is that there's a truth to this, and that's how he's referencing beauty here. And object-oriented ontology rejects the idea that human existence should prevail over the existence of non-human objects. It claims that things are not component to other things; they have their own unique existence, and that's also something we can all consider as we consider the Hodges effect. The idea of space dust comes out of the idea of museum dust, and that's something that I did in the 90s. I started collecting art museum dust, and the idea of being an exhibition technician changed my response to the dust that had fallen, because it was made of the art that was falling from the artwork that I was kind of protecting in the museum. And as a result, it created this kind of like different way of looking at it, where it related to additive and reductive sculpture. Reductive sculpture would be the dust that falls away from the artwork, or the fiber that fell off of an African sculpture I saw. So art museum dust suddenly became much more complex because it's a hybrid of the art, the institution, audience, artists themselves, and art administrators. And this is an example of art museum dust from the Pompidou Center, done with microscopy. So the Earth rose fatter every day, snowed under a continuous microscopic flurry of space specks. An average, every square yard of the planet should nonetheless receive 1 speck a day. Lie on your lawn for a day and you stand a shot of being pelted with a glassy mini marble or a delicate crumb of comet dust. And according to a 2021 study published in Earth and Planetary Science, researchers say about 5,200 metric tons of micrometeorites fall on the Earth each year. One of the ways that you can create Hodges effect for yourself is by using magnets and putting them in the downspouts of your house. That way you can have the Hodges effect on your own, and you don't have to be a famous astronaut or NASA scientist to do that. So I hope that you consider how fast we're moving on the planet, our orbit, and your place in the cosmos, and help support this. My response to the way I got Hodges effect is from being born 150 miles from where Ann Hodges was living in Alabama. And my dad was working for the space program with Northrop Laboratories and Boeing. And so that's kind of how I come into it. So it's a pleasure to be putting up work here and at University of Florida, and having work in Ireland as well to commemorate Ann Hodges Day. One day we knew this would fall on us. So you can do these different exercises like lunar wave, which I'll leave up for just a second, and sign the petition. And thank you.
Thank you, Sean. Really, really interesting. And I believe Julia will be joining us very shortly to.
We're hooking up.
Yeah. She'll be talking a little bit more about the science of the asteroids or the meteorites themselves, I believe.
All right, can you guys see that?
Yes, thanks, Julia. Yeah.
Mic in pocket, mic clothing. All right, great. Well, thanks so much for Sean and Sean for organizing this. I'm really pleased to be here to be talking about it. I'm going to move this forward. My name is Julia, and my background is in planetary sciences, and I kind of wanted to give you guys a bit of an intro into what it is that we see as planetary sciences or planetary scientists, and what it is that we do to kind of in terms of our work. So the first thing to kind of talk about really is, what is a meteorite? That's probably a bit of an obvious one, but it's always a good idea to start with a bit of a definition. So from my perspective, a meteorite, it's a chunk of rock that I get to study, which is awesome. But they're mostly rocks that come from the asteroid belt, and some of them come from the moon, and some of them come from Mars as well. But these things have survived the passage through space, and they've survived the passage through the Earth's atmosphere, and they've landed on the surface of the Earth and have subsequently been recovered. So these are basically fragments of extraterrestrial materials. These are things that come from different places, and they also represent these massive kind of snapshots of major solar system processes. So they are like keys to our past. It's really, really exciting. There are also many different types of meteorites. I've got a couple of pictures on the screen just here. If I can navigate to that. No, I can. There we go. So we've got one of these, which is a chondrite. So that's a type of meteorite that contains some of the earliest materials from which our solar system formed. So those include things like chondrules and calcium, aluminium rich inclusions. And on the right, we've got a kind of zoom in and zoom out of part of the meteorite collection that is based at Arizona State University. And these are mainly kind of more iron meteorites. They have been through planet forming processes. So we've got some separation of some of the different elements. So you've got a lot of ions grouping together, and you've got silicates grouping somewhere else, which is essentially what happened to our Earth, where it created our different layers. You've got the Earth's core. This is what these types of iron meteorites represent. Then as you go further out, you've got those much more like lighter materials. So that's generally speaking what I mean when I'm talking about a meteorite. What is a meteorite? One of these fantastic pieces of rock that I get to study. So I wanted to run through a couple of other definitions as well, because it's a good idea just to make sure that we haven't got our kind of tongues twisted, because they're very similar words, and it can be pretty easy to get them mixed up. So we've talked about what a meteorite is. So what is a meteor? Well, technically speaking, a meteor is what I class as an event, or it's like a light and sound event that is associated with the passage of a rock as it's coming through the Earth's atmosphere. If that passage is particularly spicy, if you've got a lot of energy going on there, then actually you can look like a fireball in the sky, which is really exciting. Now, typically we have a couple of other phrases that we use to describe these rocky materials before they get to us here on the Earth. We call them meteoroids or asteroids, depending on their size. So again, we've got some similar words: meteoroid, meteor, and meteorite. Ultimately, the meteorite is the word we give to the rock once it's recovered. But before then, when it's not actually hit anything, it's still technically a meteoroid, then going through a meteor event. We also have an impact crater. That's another term we use in planetary sciences, and that's usually the word we give to describe the kind of scar left in the ground afterwards. And the size of that crater will depend on the size of the material and also what it's being impacted into. We also have another phrase that we use that is a strewn field, and that is a phrase we use to describe how the rocks are distributed during a meteor event. So you can have a huge area in a locality that can be covered in different bits of meteorite eventually that are recovered. So, okay, I've given some definitions. I've talked a little bit about what meteorites are, but where exactly do we find them? Who has them? Who has these meteorites? Well, a lot of them are in institutions and general collections. That might be museums or other sorts of areas where they've been curated. There are major institutions like NASA, as well as ESA and JAXA. So that's the North American Space Agency. Sorry, then I'm getting all my acronyms mixed up. I'm totally blanking on what NASA stands for, so that's amazing. ESA is the European Space Agency, and JAXA is the Japanese Space Agency. So these are facilities that house and hold a lot of these meteorites in collections. Some people collect these as well. They are actually, people own them because they are artifacts in some way. So that's another place where we have them. And there's also collections within different universities for researchers like myself who might work on them. And we also have people who can help acquire or sell materials, and that might be a meteorite dealer. So we have thousands and thousands of these things, which is wonderful. And we've got more arriving all the time, which is also great because it means that there's more things to study. Ultimately, analyzing these meteorites and doing that in the laboratory is a much better cost-effective measure of trying to explore space. Gravity is doing the work for us. Thank you very much, gravity. The rocks are being delivered, not exactly to me, sat in my lab waiting for something to fall through the roof, but I'm able to acquire these materials and do research on them without having to spend billions of dollars or pounds or euros going into space to acquire materials. Now, there are some missions that have started to bring back materials now, which is really fantastic. So we're actually able to start kind of standardizing and saying, hey, this belongs over here, this belongs over here. Those missions are very, very costly, but they bring back amazing data. So as we continue on, we are having more of these kind of sample return or in situ analyses taking place. So that's really, really wonderful. But for now, a lot of our research can be done within the laboratory environment. Okay, so where exactly are they from? I've told you where you can find them here on the Earth, but where are they from? So I would propose that somewhere in our solar system, fairly far away. We have some localities where these are based. Most of them are actually in what we call the asteroid belt, which is an area between Mars and Jupiter, where a lot of these materials are kind of congregated. It's effectively like a disco for your kind of juvenile rocks. So they're all hanging out there, having a fairly good time. So how do they end up here? Well, you need some sort of collision to have taken place, and that's not kind of unusual necessarily, because you've got all these kind of rocky things kind of moving around, but some sort of collision has to take place. These things have to get knocked out of their kind of stable area, and then they can be ejected. And when these things are ejected, they have to go somewhere. And where are they going to go? Well, they're going to go towards something that has mass. So a rock has mass, and typically with anything that has a mass, it'll want to be near anything else that has mass. And that's like me getting home and being on my sofa. I want to be near something. So it's the same kind of thing with rocky objects. So when you have an ejection of something from the asteroid belt, it's going to go towards something with large mass. And one of the biggest things in our solar system, in fact, the biggest thing in our solar system, is actually the sun. And luckily for us, between the asteroid belt and the sun is where the Earth is. That's where we're hanging out. So we're able to get some things come in and actually kind of collide with us here. Okay. So generally speaking, a lot of ejected materials can spend quite a long time hanging out in space before they actually get to us here. Most of these materials are actually affected by what you might call damage. They're damaged, they're affected by cosmic rays coming in. And we're able to establish something called a cosmic ray exposure, which gives us an age of a sample. So what we have going on is we have this kind of space damage. Cosmic rays are coming in all the time from the sun and also other star-like objects, and they're causing damage to the surfaces of these meteorites. And what we're able to do as geochemists or planetary scientists is we're able to go in and we're able to measure the amount of this damage that's taken place. And then that can give us information about how long that meteorite was in space being damaged before it got here, and that can tell us the time frame it took to get here, which is really cool and groovy. So for something to become a meteorite, it does have to collide with the Earth and then be recovered. And sometimes we're lucky enough to actually see that taking place. So we have a fairly impressive, we'll play that again, we have a fairly impressive meteor coming in here. This is the Peekskill fireball that happened in 1992. It was caught on film taking place during a football game. So there were a lot of spectators, which is really cool. And you'll see that some of the different fragments are kind of breaking off. Now, in terms of a radiant point, it's really important to, like Sean gave a great introduction about how that works. It's really important to consider where you are as the observer. In this case, the radiant point of where this was coming in, to find that, we'd have to be in its path, in its collision path. We're actually seeing it from a different locality in that sense. So things are kind of splitting off in that one direction. So for the radiant point to kind of work, you have to be observing this thing coming in. And you can kind of think about it as well. If you ever go out to anywhere that's more kind of desert-like, that has large plains, if you see like a really straight road, if you're standing in the middle of the road, I wouldn't advise it if there's traffic, but if you're standing in the middle of a road, you can probably see it kind of everything kind of coming down to this single point. It's almost the same thing. In this case, you're standing to the side of the road and watching this come in. Okay. Ooh, where's my mouse? Okay, so for those meteoroids or materials that are large enough and come in and cause some damage, they can actually leave a bit of a, you know, a kind of calling card on the surface of the Earth, and that's where we get our impact craters. And much like the musical piece that Sean has developed, we actually see those exact same shapes forming, not necessarily on a musical score, but we do see that happening on a surface. So this is an idea where we've had a meteor come in, we've had it impact the surface, and then we have this change in the environment. So it is a fairly dynamic process. We have a lot of changes going in. And the amount of damage that takes place on this surface is fully proportional to the size of that object coming in. And you can imagine the larger the object, the more damage that can take place. So this can be fairly substantial. And I'd like you to just kind of think about this when we're considering what happened to Ann Hodges. We had an object come through the Earth's atmosphere and impact with her. So in some way, what we're seeing, these images of this impact crater taking place, happened to her in some small effect on her actual physical body. So that's pretty kind of astounding. All right, so we see evidence for lots of different impact craters on the Earth. You can go out and map them. Thank you to Google Maps and other sorts of things, because it's made that a little bit easier to do. Often if you see a large round circular object, you're like, oh, maybe. So we're able to at least establish that, yes, the Earth has been impacted fairly heavily. It is also important to know that the surface of the Earth is about 70% covered in water in some form. So it's also quite likely that while we have preserved a load of impacts, we've had a lot probably go into the oceans as well. Another fairly important thing to note too is whether we actually have a complete record of our impact history. And the answer to that is probably no. And that's because the Earth is a fantastic planet that has this thing called plate tectonics. It's like a big kind of rocky recycling process where the very upper layers of our Earth, the crust, are sliding around and moving around and constantly being recycled. So we have preserved some history, but we don't have the entire history of what happened to our planet. If we look at other planetary bodies that don't have plate tectonics, you can see that they are significantly more cratered. So that gives us another, like, it gives us these hints about all this dynamic stuff that was happening in our solar system. Really fascinating. And we can also take a look, going back to the Earth, we can take a look and try to consider what the likelihood, the statistical probability of an impact taking place will be, depending on the size of the crater. And again, that's based on going out and mapping everything. Now, if we don't have all the craters mapped in the world, we probably miss some. Those numbers might not be totally accurate, but we can at least try and come down and say, okay, well, statistically speaking, over 1 million years, we should have had this number of impacts, which is also kind of scary, I guess, in a way. And if you're interested in that sort of thing, or if you're interested in learning a little bit more, there are a load of resources online that you can go for. And there's an institute called the Lunar Planetary Institute, and they've got some information on that. There's a web page that you can follow there. All right. So as I said, we do find impacts in other places in our solar system as well. And typically those craters that are formed are fairly almost pristine because they're not being weathered away or damaged by processes on the Earth that we have, like water and wind movement. So those craters can look really, really fresh, even though they might be millions and millions, if not billions of years old, which is kind of really exciting. What I think is really interesting is that we are basically seeing the same pattern happening in different places. The craters look the same, right? No matter where these impacts are taking place. And again, thinking back to Ann Hodges, she had effectively, at some point during that impact, she had probably had a crater on her, which I think is kind of fascinating. All right, so I wanted to talk a little bit about what happens when an impact event takes place. Now, the numbers on this diagram are not entirely accurate, but it's just to give you kind of a bit of a visual representation of about what takes place. And this was actually drawn by one of my very close friends, who is the curator at the Arizona State University and the Center for Meteoritics there, Dr. Lawrence Garvey. And he drew this out, and I really like that. In fact, he's effectively added Mrs. Hodges to this because one of the stick figures has, in fact, or is about to be impacted by a rock. So what we have is, as a meteoroid is coming through the atmosphere, it starts going through some fairly significant changes. It's been out in space. It's not been bothering many people. There's not been anything going on. It's not really had anything to interact with. And suddenly it starts seeing this atmosphere and it's like, what is this? So things start changing. It's going at some fairly high speeds. It starts interacting with something that's got much more density. So things start changing a little bit. We start getting a bit of heat. But what's really interesting is that the heat that is being formed, and if you have a large enough sample or large enough rock, I think it's calling them sample. The samples to me because they're in my lab, but a large enough rock, as you're having that come through the atmosphere, you end up with a pressure differential from the size and the speed of the rock coming through and the air in front of this rock. So you end up basically forcing high pressures in front of this rock, and that causes this massive heating event, and it effectively not erupts, but it causes a kind of flaming event around the outside of the meteoroid, making it look like a fireball as it's coming in. Now, this only happens to typically the larger samples. Some of the smaller ones can kind of get away with not necessarily looking all flamey, and there's a couple of reasons for that, which are heavily based on physics, the gravity of the material, the mass of the material, how it's coming in, that sort of thing. Ultimately, you have a rock, it's coming in, it's coming through the atmosphere, it's going through a massive reduction in speed, it's really slowing down fairly significantly, and it's usually within those first few seconds that you're seeing this fairly massive fireball. And if anyone's ever seen a meteor event take place, it doesn't take an hour, it takes minutes, seconds to minutes to take place. So you'll be seeing this happening, and then at some point it'll reach what you might call a kind of dark flight. And this is the point at which you can no longer see the meteor event taking place, the flames have stopped, and then the meteor is on its way to a path and you probably won't know necessarily where it's going to be landing. All right. So I mentioned that you've got this big heat differential and what happens to the rock as this is taking place. When you recover a sample after, or a rock or a meteorite after an event, you'll find it glistening. It'll have what's called especially if it's a really fresh fall, it'll be glistening around the outside because those outside nanometer, micrometer layers of that meteorite have been superheated. So it looks like a varnish. And it's really, really impressive. And the freshest sample I saw, I observed it 2 or 3 days after it fallen, and it literally looked like it was sparkling. It's really, really impressive. This is what we call the fusion crust. So that's another really big diagnostic thing for planetary scientists. If you think you've got something that might be a meteorite, the fusion crust is often going to be something that you're going to go and try to classify or determine. There it is. So I've got a little video of a meteor event taking place. This was a fairly notable one. It happened in 2013, so we're going on nearly 10 years ago, but it was a fairly impressive event. So this was caught on some dash cams. So you can see this coming in. Again, we're not seeing the radiant points. We're not physically looking directly at it as it's coming at us. But you can kind of see this coming. You see this kind of like almost like fireball events. When that does happen, some of the materials do kind of break up into smaller pieces. So you can start seeing things kind of falling out. This is another view from that a little bit in a different angle. You see this come in, and the light change is mainly the camera changing based on the amount of light that it's experiencing. So I was really surprised by maybe it's just because I get really excited by meteorites. I would have been like, oh my goodness, and they're like, oh, look at that. So I thought that was quite interesting. Okay, so this is what we call the strewn field of this area. And you can hopefully see a couple of lines on this diagram. So one of them is the predicted line of where they thought the event was taking place in the trajectory, and then there are other lines on there that relate to where they think the biggest mass was of materials that were being dropped and then subsequently could be recovered from. There's lots of little dots on this diagram as well. Ultimately, if you look at this line, you can see that we've got a couple of potential, not hazards, but there's a few things in the way that might maybe stop recovery working out as well as we might like it to. This is definitely what happened in this case, because the main mass from this event landed in this lake. And you can see this lovely kind of crater that was formed, but it was a crater formed in some ice. So they were able to go out and they sent divers in to kind of recover this material. So they got this kind of partial impactor think it weighed about 570 kilograms. I don't know what that is in pounds. I'm not very good at converting my units, but this is very heavy. It actually ultimately broke into multiple pieces when they tried to load it to take it away to be studied. Now, a lot of much smaller pieces were subsequently recovered. We've got some in the lab upstairs. They're really, really cute. So a lot of different types of material, well, not different types, but lots of different sizes of materials were recovered. So, I mean, arguably, many of the residents in Chelyabinsk were probably affected by small things coming down. They may not have even realized it. Another great thing that helped with the recovery in this scenario is that a lot of these materials fell in icy areas, so they were able to go and find them subsequently, which was really useful. Okay, so speaking of kind of recovering materials, meteorites don't always land on the ground necessarily. So here's an image of a fairly famous vehicle that was impacted by a meteor event. And this is a really great way of effectively, hopefully, increasing your car's value. So how to take a car that's worth however many hundreds of dollars and turn it into a car that's worth many, many more dollars, and would probably be, well, at some point this was acquired by a museum and has been subsequently lent out. I mean, it's a very, very, impressive artifact in itself. Certainly not something that you should be climbing inside of and taking selfies with, but there we go. I got permission to do this, so it was all right. So another thing to talk about is where we get these things and how do we recover them. Well, we find them in places where they're fairly obvious to find. So materials are falling all the time. There isn't necessarily a massive bias about where they go, but where there is a bias is in terms of how they are recovered. We find them in places where they're very easy to spot. So we might find them on glaciers, we might find them on ice sheets, because we've got a very light background with something really, really dark on top of it. We might find them in desert environments where they're very, very easy to spot. So we've got a little praying mantis in this upper image here, guarding a very, very small meteorite fragment, and then the bottom picture is a colleague and friend of mine, Dr. Caroline Smith, who is one of the creators at the Natural Museum in London. And just by her knee, her right knee, there's a small penknife, and right next to that penknife is a tiny fragment, a tiny little meteorite that has been recovered. All right. So kind of on to Sylacauga. So speaking of places where these things tend to impact, as we know, we had a fairly major event happen here a number of years ago now, where a meteoroid material, a rock, came through the roof of Mrs. Ann Hodges' house as she was taking a nap. It came through, it hit the stand-up radio, and then it ricocheted across the room and hit her in the abdomen, arm, and hip area. Wow, that's a fairly impressive thing to have happened. She certainly bore the brunt of a fairly massive impact. You might be able to see, sorry, things over here just switched off earlier. Okay, it could be, as I said, that she might have had a crater in her at some point, which is kind of really quite fascinating. I actually have the Sylacauga meteorite with me here today, so I can get that out and put the lights back up if that's of interest to anybody to look at. I do want to also draw some comparison with a meteor event that happened about a year ago, actually almost exactly a year ago, which is kind of really interesting and coincidental. It has some similarities. So in Ontario, in Canada, a meteor came through the roof of somebody's house. I think they may have also been sleeping, but they were sleeping in bed. And the lady realized that something had happened and found a meteorite next to her, under her pillow, which is really quite fascinating. So I felt that this story kind of has some similarities to what happened in the case of the Sylacauga meteorite and Hodges. All right. So the next thing to talk about, just kind of conclude, is what do I do then as a planetary scientist? I look at these materials at the micrometer scale, sometimes at the nanometer scale. So I'm interested in trying to learn about them by looking at them under the microscope. I've got some images here of the single thin section that we have of Sylacauga meteorite, which is within the collections of the Alabama Museum of Natural History here. It's a really wonderful section. It's got some really lovely examples of some of these chondritic phases, some of these early things that formed in our solar system's history. This wonderful round object in the kind of top corner there, that is what we call a chondrule. This is one of my favorite images. I actually have this on my desktop computer. I think it's really great. But we have some other interesting materials going on as well. Now, a point that was brought up earlier, I think it was by Sean, was that this meteorite is interesting. It's a meteorite. Most meteorites do have some interest. But the main thing about this is that it impacted a person. That's what has given it such notoriety and made it really into this unique object. But we are able to look at these things through a lens under the microscope and hopefully understand more about how they formed. Here are a couple of other images that I have of samples that I look at. So these ones have gone through different processes. You'll see that they look totally different. These things have gone through planet forming processes that have a very different look to them. That's all I have right now. So thank you for listening.
Thanks so much, folks. It's been really interesting. I did have one question myself, actually, for all you guys, I guess. During Sean Miller's talk, he pointed out how at the time that the meteor struck Ann Hodges, there was only 2 billion people on the planet. And as we're pushing towards 8 billion now, I mean, the number of meteorites passing through the atmosphere doesn't seem to be decreasing, but the number of people seems to be increasing. And Julie, you've posted a couple of near misses just there. How long do you think it's going to be before we see a second Ann Hodges? And if it does happen, what would that mean for the Hodges effect, do you think? Perhaps Sean Taylor, you could weigh in first.
That's a very interesting question. And yes, it's something we could speculate on, isn't it? That the law of averages actually would probably suggest, and if I was a betting man, which I probably am, that the likelihood of somebody else getting hit by a meteorite, although it does seem to favor the female of our species for some reason, so maybe that would narrow the odds. So what would I say? Maybe a 10 to 1 chance, an outside chance of more than one person getting hit, maybe 20 to 1 chance that they're not female. I'd like to maybe frame it that way. But certainly that's an interesting observation, and one that would severely impact upon this attempt to make a case solely for Ann Hodges for a day to be named after her. Then we'd have to start introducing other names, which would be quite complex, I think.
Julia or Sean, you guys any thoughts on that?
Yeah, can you hear me?
Yep.
I was talking with John Friel, the director of the Natural History Museum, about this yesterday. Like he was wondering if when it happens again, if then does that kind of take the intrigue away from the Ann Hodges if it does happen. But then also he brought up a really good point, and it's a really interesting point, that part of the thing that makes the Ann Hodges story so important is that just the way that Life magazine got those images out so fast, and they're so compelling. In the bed, all that stuff. It's just you hear the story, you don't believe it, and then the photos do such a good job of illustrating, wow, it really happened and it was big, So I don't think the Ann Hodges story will ever lose its kind of magic. And also, from just a perspective of when you think about class and when you think about being a woman at that time in the 50s, I mean, I think that was really rough. I think there's something today about the internet, just the way she was inundated with letters and people invading her home and all that stuff. Today it would go out over the internet so quick, and then the person would be all over the internet talking about it. Everybody would be a little more satisfied. But at the time, I think it was probably pretty devastating for her. So that's my thoughts.
Julia?
Hi, we do sometimes get reports of, well, a couple of years ago, we had a potential report that someone had been hit by something, and it turned out not to be the case. They said, oh, I was knocked off my bicycle, by something that happened, but it turned out to be not the case. But I think that's also another aspect of this, that there is this kind of fascination with the idea of being impacted by something. I think we see this a lot in popular culture. It's a big theme for many kind of sci-fi related things too. So that's something to consider. I mean, I think I concur. I mean, I definitely concur with my friends and colleagues here that Mrs. Hodges is a very special person. This event happening to her, as unfortunate as it was a very special event, and I don't think that further. I don't think that future events would take away from that. I think it may provide us some way of making a massive comparison, just as Sean has just said. You know, like the images getting out in the newspapers and the Life magazine as quickly. That's almost the same as, or very similar to, or the equivalent of an Instagram post going out, like almost immediately something like that happening. And I also agree that, like, we know how much social media plays a part in telling stories these days. And it would be really interesting to see how that would play out in itself, in a different scenario. But yeah, no, I mean, this is still a very, like, it's a very special rock. It's got a lot of meaning to people here in Alabama as well. So I think it really does, you know, it's like, we're not annoyed or upset with Neil Armstrong for having gone to the moon and not being the only person to go there, right? So like, it's still a major event that happened.
Absolutely. I mean, I've worked in an observatory now for 4 years, and if you ask me who the third man to step on the moon was, I couldn't tell you. So there is certainly some strong association with being the first to do something. So yeah, I don't think there is any risk of Ann Hodges being forgotten. But we all obviously all agree that we would like to do more to remember. So for you folks watching at home, we've mentioned a petition several times here that we are hoping to have the date marked as the Ann Hodges Day. If you're looking to find that petition, you can find the link under the YouTube video that you're watching's description. And if you're looking to learn more about this, you can visit our website. The Hodges Affects the Radiant Point event page has a lot more information as well. And I'd just like to wrap up by thanking all of our guests for joining us today, and to everybody who's watching at home. So with that, I'll bid you all adieu. Thanks very much, and see you all again soon.
Thank you.
Thank you.
Waving to the
Happy Ann Hodges Day.
Happy